Good morning. Uh, I think this is the last discussion. The torsion for homogeneous linearly elastic bars. Okay, so there are at least two formulations that we are going to see a lot in torsion. The first one is the tau, relations with the torsion and the inertia, and also the angle, the twist angle is also the torsion and inertia inside within the formula. So these two formula will be, I think, we are going to use it a lot in solving most of the problems. Okay, and then this is also the example on how to use the formula, right? So we have a homogeneous like a rod or shaft, a tubular shaft, and basically we are going to compute the inertia both materials, the hollow shaft and the solids, and then we are going to use it into our formula, and then we get the tau, and then we get the twist angle. Okay. Okay. And then it's asking the ratio of the weight, and we get the idea of that. Okay. Okay. Okay, let me go through some sort of we call it the distribution, okay, the stress distribution. So if we take this as our shear stress scheme. This is usually we write like this, and this goes down and this goes right. And then let's say we are going to have some changes in this angle. Okay, and then let's take this this angle and let's analyze. So that's the angle, and then this is the tau. This is the tau here. And we have also shear stress, that is going to be the internal force. Okay. And we have the normal here. Or maybe let me write, this is the sigma within the normal. This is the normal from the perspective on this diagonal area. Okay, and then this tau here, tau, this is the normal. So when we have the sigma, this is Fr, and we say that the positive is the one that is going there, then we can based on the angle, we can rewrite this tau as tau an cosine theta and this will be tau an sine theta. And this is, we can rewrite as tau dan, and then this can be written as sigma an. Perhaps I think it's best if you, this is coming from the tubular or the rod that is this rod like that. So we slice some part of it. So this is going to be this area here. This is area. Okay. And then this will be the tau. So that's how it goes. Okay, so this will be that. Okay. And then let's say this is the central, and we have the torsion going there, torsion going there. This is the x-axis. Okay. So we say that this is the x, right, the x-axis, and based on the normal that is here, this is going to be the t, and this will be the angle theta. Okay. So we are taking this A here, the area, and then we have that. We can also take this sigma for n, okay, which means that this is going to be that way, positive, according to the x-axis. This will be equal to so sigma is equal -2 tau sine theta cosine theta. And this part here, let me move down side here. This is equal to tau so cosine theta and then cosine theta, so cosine squared plus tau sine squared theta Okay, now this can be written with the double angle formula. This is going to be negative tau sine 2 theta. This is negative tau cosine 2 theta. So we have this formula, okay, both for the sigma and the tau. And based on this, then the maximum value will be attained when theta is 45
45 degree, right? Maximum value of tau, tau. And maximum value of sigma will be attained for, oh, sorry, this is 90, this is 90. This is 90, this is 45. Right, sigma is sine will be max if it's 90, so 45, right? Okay. So this is the conclusions, okay, based on the formula. So this is the sigma, this is the tau. So we can rewrite the sigma using the tau that is defined in the picture, and then using sine to theta, and we can rewrite the tau, that is in the internal within the bar, and we can rewrite as negative tau cosine to theta. Okay, you will see that this angle, we get the angle 90 and 45. This special angle will be important in the future studies, as we are going to see the relations between the sigma and the tau in more details with the Mohr circle. If you have ever heard the Mohr circle, it is how to predict when will the failure happens, okay, when failure happens within the torsion or within the axial stress. Okay. So if you try to find chalk, okay, chalk to write the board, if you twist and if you maybe make some stress using axial stress, you will see differences in the angle. If you twist, imagine you twist the chalk, which is the brittle material, right? Chalk is brittle material. You will see that it will make 45 degree. Okay. I forgot to bring chalk. Maybe next week I will try to use that and try to demonstrate. And you will see that the failure is on when the chalk is on 45 degrees. It's really simple demonstrations to show the importance of this angle. Okay. Now that is the stress distributions. Another important thing is the strain. Okay. So the strain distribution So first we are going to relate the strain using the tau. G is the shear modulus, right? This is the shear strain that usually we are going to see the change in angle, right? This is the shear stress. Okay, now based on our schematic diagram for the tau. And then when the strain happen and the maximum value is happening, we can draw this square as this. And we can imagine that this will be that way.
So suppose that this is going to be going there, and this part here is going over.
So this is when the angle is 45 degrees. So this is when the maximum value, or in our case here, this is the maximum compression on this way, and this will be the maximum tension. Now, based on this compression and the tension, we can write the strain for 45 degree by using the, I think, formula from previous terms, previous sections. So over E, and then 1 plus the Poisson ratio. And we also can write the negative part of the 45 degree as so we can write these two strain that is related to the compression and the tension. So this will be the tension, okay, tension. This is compression. Or to help you simplify the problem, we can write down this part here. So E max compression is equal 45 negative tau over 2G. And the strain max for tension, this is for the negative 45 degree and positive. How we get the 45 and negative 45, you can see from this part here. This is going over there. This is negative 45, right?
The negative positive means how the strain changes. So this is the original shape, and it's changed, becomes this. So if you see from the normal size, it goes positive angle. Right? Goes positive angle becomes this, and this goes going clockwise, which is negative angle, right? In the polar. So you get the positive 45 and negative 45. And we can say that this will be related to our tension here, which is negative 45, this maximum tension. The strain will be negative 45. The maximum for compression will be 45. Okay. The state of the shear stress, we are going to see a lot later on. I think maybe in near the end of the chapter, probably.
So basically, we are going to use the formula for the strain by using this two approach. Depends on the conditions, what will happen. So torsion, when we apply torsion into the system, we can have a compression or tension. Okay? And then depends on how complex the system will be, then we are going to decide which are bigger, the torsion, the compression or the tension. Let me give you notes that from this angle, as I said, the chalk will make 45 degrees if you try to rotate, try to put torsion. So brittle materials it will be weaker in torsion, while ductile weaker in shear. If you have ever seen the torsion testing for let's say steel, if you imagine steel and you give torsion, you will see that it will twist, and later when it's failed, when it's broken, you will see that it's making the 90 degree. That's the ductile material. But the brittle, you can imagine with the chalkboard. Before you ever start to like give more force and you try to take torsion, it's already broken. And you'll see that the angle, you will see the angle when you try. So imagine that this is chalk, and you give torsion. Okay, you will see that this will be broken into like this, and this angle here is 45 degrees, and you can prove that. You can prove that if you ever take chalk, try to torsion. You will see that it will break this chalk, it will become this two, and this angle will be 45. That is how we visualize this 45. That's the maximum value that we ever have. That's the possible value, okay, for the if we try to give torsion to chalk. So that's why the brittle is weaker in torsion, but the ductile weaker in shear. Okay, weaker in shear, which means that if you have the, let's say this is chalk, this is the steel. Let's say this is steel. Steel, try to give torsion. It is not because the torsion makes the steel broken, but because the shear inside this steel. Okay, so this will give you this cut. 90 degrees. This is ductile material. This is the brittle material. Okay. This we say it's like we cut, right? But we give the torsion, but the one that makes
still cut eventually. It's not the torsion itself, but the shear that caused by this torsion.
Okay, there's an example, but I think example, it's I think we can skip the example for this one and focus on the next one that is, I think, more important. Okay, let's move on to next section, which is the statically determinate uniform torsion members. Remember that we start with the twist angle for some members is equal to L G I. So this is the angle, or we could say the twisting angle. Remember, T is for torsion, L is for length. This is the modulus. This is the inertia. We can somehow also relate this angle becomes the element, force element, like this. But I don't think this is going to help a lot, but I think it's simplified some equations. But this is actually the same thing. So if you just want to keep just the first formula, that's okay. It's the same thing. Now if you look on the picture, I think let me write the picture, maybe moving a little bit here. Okay, so on the left side, the picture say that this is the statically determinate assemblage, which means that we could figure it out from the torsion that is in each members. Okay, but for the right picture, we call it statically indeterminate assemblage. This is similar to from the chapter 3 that we have done. Statically means that we know all the information from the members, but in here, we give this only maybe one torsion, and then we need to figure out what will be the other part of the system, which means that we need to write down or make maybe some assumptions or maybe some relations, how to make sure that we know this part. Okay. Like for example, in chapter 3, usually when we have walls, like in your exam question, then we need to take the assumption that the elongation is going to be restricted because of the wall. So all the elongation will be equal to 0. This is also the same. Okay? We can also make this relations with some equations to relate all the things, and then we can solve the problem. Okay. Well, let's start from this part first. Okay. Let's start from the left picture, which is the statically determinate assemblage. So we start from the sign convention. As usual, the sign convention at the end of the day, it can be up to you, okay? You can take the clockwise, counterclockwise to make it positive, as long as you are consistent for your calculations. But for now, let's say we are going to take this sign conventions as a positive sign, if you see the picture. So when we rotate according to that rotations, then it's the positive sides, okay? And then all the things that goes by this rotations, then we can use our right hand to make sure that, okay, we get this, and this is going to be, we can write the positive or negative. Okay, we can follow up the right hand rule to make sure that we are able to connect this sign convention. Okay, perhaps one example for this part. Okay. So let me write these notes. Select direction for positive x and the positive torque and positive rotation will follow the right hand rule. So it's up to you. If you choose the x directions positive, maybe here, then we make this positive. We make this positive. But either way, it's still, you can still be able to calculate. Okay? But perhaps at the end, maybe this sign will be opposite. Then it is still okay as long as you understand. Okay, perhaps an example can be looked up, okay, for the statically determinate uniform torsion members. Yeah, I haven't checked all the exam. I think I checked 2 or 3. Seems still okay. Yeah, around 50 to 60, I think, score. Yeah, 60 something and 50 something. I think that's still okay. I think you've got it right for the first 2 questions, most of you. And then third and fourth, a little bit mistake at the process, but then the whole thing, the whole questions or the whole information becomes not really clear, okay? Because of the I think missing something in the assumption. Okay, let me give you an example. So let's say we have, let me draw. Okay, this is the 1, this is 2, this is C, this is B, this is A. This is the axis. So let me just give you the x over there. So the torsions over here will be positive torsion. So this is, let's say this is TA. This is at A, okay, maybe let me write there. Maybe let me make it closer. TA with the angle A. This is TB with the angle B. And we have distance L2 and L1. So we have a two-element torsion, and TN and TB. This is external torques at A and B, and this angle, our rotation angle. So first determine internal resisting torques. It's similar thing what we decide to take the internal force like before in material 1 and 2, and determine the rotation angle at A and B. So first we take the sigma moment for x equals 0. Let's say we are going to divide these members by the material. So let's say this is the material 1. Okay, so we focus only for material 1. So we have TA, and to make this equal 0, we need to make another T1, that is the internal torsion or the internal resisting torques, that is going to be TA is positive and T1 is negative, right? So it's going to be, let's say we cut this part. So if this is TA, then this is going to be the T1, okay? So this is equal to 0. And then for material 2, also the same. The sigma moment with the x as our basis for the rotations. This will be, let's make a little bit bigger. So if we have TB, that is going to be here, then we are going to have T2, okay? And also we have the TA, right? The TA also makes reaction with the material 2, don't forget that. So this will be TA. So now we have TA plus TB minus T2 equal to 0, okay? So T1 is TA equal to TA, and T2 is equal to TA plus TB, okay? And I think this is logically can be understood from the picture, that if you think from this part of number 2 is affected by this TA and TB directly, right? But if we cut this 1, then we see that the material 1 will be affected by this TA, okay? Now, based on our free body diagram that we have this part here, we can write down that the angle, or maybe let me write in the new page, and let me copy this part here, copy, and then copy this part also. Okay, now from here we get that the angle of A, or perhaps start from here. We can write the angle member is the F, the and T, the torsion. The rotation's angle, then we get this is the twisted angle of A is equal to twisted angle of 1 plus twisted angle of 2, and twisted angle B is equal to twisted angle of 2. So from this part we get TAL1 G1 inertia for material 1 plus TA TB this is G2 inertia 2, and then twisted angle B is TB or TA plus TB okay. Or perhaps to understand why we get this plus, we can relate to that the twisted angle 1 is twisted angle in A minus twisted angle in B, okay. And twisted angle 2 is twisted angle in B minus twisted angle in C. And since there's no twisted angle in C because of the wall, we get this just twisted angle B. So that's why it's going to be equal to 2, and this is 1 plus 2. Okay, so because there is a torsion A and torsion B that is changing the twisted angle for both sides, for both A and B, there will be some differences in the material 1, but in material 2, this is going to be B and C, but C is, we can assume C is 0 because of the wall, then this is going to be just twisted angle B for the material 2. Okay, there's another example, but I think I will just skip that into next week. And then next week we'll be focused on the indeterminate torsion bar. So I think I will just stop until here.